much taller than that? 6'3", 6'4"? Yes, there are people who are 6'3", 6'4", but not as many, okay? Men who are shorter than the average. So men who are 5'2", 5'3", okay? There are men who are around 5'2", 5'3", but also less common, okay? Most common will be men who are around 5'9", 5'10", and things that are close to that middle height, okay, average height-ish. Okay, so heights of people fit this. Okay, so that would be a symmetric shape there. Is that okay? And we could just summarize the symmetric shape with just a simple curve that looks like that also. That would also count as symmetric. Okay, I can draw a histogram that looks like this. Okay, this we would call right skewed. And we might draw, to summarize it, we might just say it looks like this. Okay, what does it mean here? This means values over here, these are the most common values. Okay. And are there people who are way higher? Yes, not very many, but there are people who are much, much higher than this most common area. Okay, quote, quote, middle-ish, average. Whereas, do we have anyone who is that much lower? No. Okay. So an example of this would be something like income. Income is right skewed. Okay. So most common household income, something is around $50,000. Okay. And then you have people who make less than that. We'll say 0.25. People who make 100,000, 200,000, 300,000, $500,000. Are there people who make $1 million a year? Yeah. Okay. Not a lot, but yes. Okay, 1 million per year. Is there? So if we say the average household income is 50,000 a year, 1 million is how much above the average? In terms of just a sheer number. It's 950,000 more than average. Okay, so if the average income is 50,000 a year, 1 million a year is 950,000 more than average. Does anyone make 950,000 less than average?
No.
No. Okay, to make 950,000 less than average means you are losing $900,000 a year. Okay, your income, your wages is negative $900,000 per year. Now, maybe there are people who have some bad debts or something, but in terms of a wage that you're being paid, nobody is paid less than $0 per year. Okay, in terms of wages. Okay, so it is possible to be way above average. Okay, so if this is the average area. Okay, so here we can be, there are people, what this indicates is, there are people who are are way above average. Okay. But if we go that far down below average, we would have no one. Okay? So this person is, this guy makes 950,000 more than average. Okay, if we go that distance below, okay, over here, we have, there's no one who is way below average. So that's what it means to be right skewed in terms of shape. Yes?
So the $1 million person would be the outlier?
Yeah, we can talk about outliers. Yes, $1 million person would be an outlier, but that's not the point of this thing. We're talking about skewness. And can you guys think of any other numeric variable that is right skewed?
The Disney Channel age range example.
Okay, Disney Channel age range. Yes, that would be right skewed. We have the average age would be, I don't know, 8 years old. Okay? The average age of the Disney Channel viewer, let's say, is 8 years old. Okay? Are there people who are way above average? Yes. Are there going to be some grandmas and grandpas watching the Disney Channel? Sure. Okay? They would be like 68 years old, 70 years old. That would be 60 years over average. Is there anybody who's watching the Disney Channel that's 60 years under average? No, because you'd have to be negative 52 years, and nobody exists that's negative 52 years old. Okay?
So if that average fell somewhere in middle age and the variance wasn't that large, could you still be less than average?
I guess the answer would be depends on your circumstance there, but okay. So yes, so Disney Channel viewers, that would be something right skewed, okay? What about recipients of Social Security?
Left skewed.
Left skewed, right skewed, okay. So you guys are already jumping to something that says left skewed, okay? So we're saying if this looks right skewed, then left skewed looks like this, okay? Is that okay? And you guys are correct. And so you guys are saying recipients of Social Security is left skewed. Is that correct or not?
Correct.
All right. I would say the answer is recipients of Social Security still right skewed, okay? How old do you have to be to receive Social Security?
65?
It's like 65 and a half, or is it 67 now? 67. I think they changed. I don't know. Is there any 55-year-olds receiving Social Security? No, not legally at least, okay? Are there any 60-year-olds receiving Social Security? There shouldn't be, okay? So the youngest person receiving Social Security should be like 65 years old or whatever the law states. Okay?
62 and a half.
62 and a half. Okay, 62 and a half. That's going to be the youngest person who can be receiving Social Security. Okay? Are there going to be 100-year-olds receiving Social Security?
Not that many.
So their answer is yes, but not very many. Okay? And why aren't there going to be very many 100-year-olds receiving Social Security?
People don't live over 100
Because there aren't very many people who are 100 years old to begin with, right? Most people die before they reach 100. That is the reality. So we're also going to see a right skewed distribution. We're not going to see, in terms of the distribution of ages, we should see no one between 0 and 62 and a half. Okay, there should be no one receiving Social Security. Then you're going to have a whole bunch of people, getting Social Security, and then just as time goes on, fewer and fewer people getting Social Security because they die off, okay? And so here we also have a right-skewed distribution that just doesn't start until 60-something, okay? So the average age of a Social Security recipient is probably like 70 years old or something, okay, 70-something years old. This would be, quote, average. Maybe we'll just say 70. Are there people who are way above average, like 99 years old? Yes, that person is 29 years over the average age of a Social Security recipient. Is there anybody receiving Social Security 29 years younger than the average? No, there shouldn't be, okay, because that would put someone at 41 or 42 years old or something.
What
Yes.
about the kids that parents died and they
This is the other thing, they
Yeah.
do have special
they have special
circumstances.
circumstances, the parents died and the kids received
Okay,
it?
all right, okay. So well, let's just say primary Social Security recipients,
Sorry.
okay? And we'll just keep it at that, okay? Yes. Life gets complicated, and our answers aren't always as clean cut as these illustrations that I want to use are.
Okay,
But
sorry.
let's just say this is what we've got going on, okay? So this is still right skewed. Okay, so just because the numbers are higher and whatnot doesn't suddenly make it left skewed. We're still right skewed. Okay, but yes, left skewed is something that looks like this. What is something that is left skewed?
It goes higher towards the end.
Higher towards the end. So that just means more common, not higher, but more common. Because higher means over here. Over here is higher and this is lower. That's just values on the number line. So the high values are common and the small values are less common. So this would be something like test scores, okay? Test scores are left skewed. Maybe the most common test score is 80% or whatever. Okay? If 80% is the average, are there people who are going to score like 30% on an exam?
Yeah.
Sure, okay. We don't like when that happens, but 30% on exam, that's 50 points below average of 80. Is there anybody who's scoring 50 points above the average of 80? No, because 50 points above average would be 130%, which is probably not possible on most tests. Yeah, I don't know very many tests that go up to 130% extra credit, but maybe, okay? Yeah. Okay, so we got something that's less skewed. Okay? So make sure you understand symmetric, right skewed, left skewed. Okay? The other part, so that's one part of describing the shape of a distribution. And the other part is the number of peaks that we have in the distribution. Okay? So when we're talking about shape, there's two parts that you have to explain. One is symmetric, right skewed, or left skewed. And then the other part, also, that you have to talk about when you're talking about shape, is unimodal, bimodal, or more than that, and we just say multimodal. Okay. Unimodal there means there's one peak. One value is most common, everything else is less common. So when it comes to the heights of people, that's going to be something that's unimodal. One, the average height is most common people around there, a lot. Other values are less common. Bimodal. Okay, we've got two peaks. This could be something like the Disney Channel viewers. A lot of kids watching the Disney Channel. Not a whole lot of 20-somethings, 20-something-year-olds watching the Disney Channel, and then we also have a lot of parents of kids watching the Disney Channel, okay? And then also not very many people who are way older than that. So we have, you know, Disney Channel viewers. So kids, their age, and then the parents, et cetera, et cetera. Okay. And then anything with more peaks than 2, you can just say multimodal. I don't know what would have that kind of shape. For sure, there might be something multimodal like that. Stock markets, you are thinking that is not going to be a variable that exhibits this. Because if you're just thinking, I'm not sure what you have in mind. I think you're thinking of like a linked time sequence of prices, which go up and down. But that's not what we're looking at here. We're looking at, let's say, different subjects, which I guess would be different companies, and we ask, what's your stock price? What's the most common stock price? Yeah, they're all over the place. You've got cheap stocks, expensive stocks. Probably the most common stocks are going to be under 10 bucks. Okay, that's probably going to be the most common price for stocks. A lot of stocks are cheaper than, but the big companies that you guys are aware of have higher values than shares. But then stock market's not a good example for numeric data just because the rules are wild. Okay, so make sure you understand how to describe the shape of a set of data, numeric data. Symmetric, right skewed, left skewed, unimodal, bimodal, multimodal. Every numeric data set, you can use 2 of those. You can use one from the left column and one from the right column to describe the shape. Okay. Now I want to talk about, we're going to get into, so that wraps up chapter 2, we're going to get into chapter 3. And we're going to start talking about numeric summaries. Numeric summaries for numeric data. Okay, listen up. We have numeric data. And, okay, so just look around your class right now, okay? Look at your other students or whatever. And just imagine trying to describe this classroom of students to someone else, okay? Now let's talk about just regarding the age of people, okay? So we're going to look at one numeric variable, and that's going to be the age of students. How would you describe the age of students in this class to someone else who's not in the class? Okay, you'd say most students are...
I'd say symmetric and unimodal.
Yeah, okay, we don't even have to talk about shape, but we just say, yeah, most of the students are going to be, looks like between ages 18 and 25, okay? And then we have a few people who are older than that. But the vast majority, I would say, between 18 and 25, okay? And we could just say something like the average age, I didn't do a survey or anything like that, but I could just say, the average age is probably around 20 years old, okay? Give or take a couple of years. If we went and surveyed everybody here. And so when we're describing, that's essentially all we're going to do with numeric summaries for data. We're just imagine trying to describe a set of data. Okay, you've got a numeric variable that you're looking at. Imagine trying to describe that to someone else. Okay, if you wanted to give the full picture, you'd have to say, oh, well, I've got this many students who are this old, and this many students who are this old, and this many people are this old, and et cetera, et cetera, et cetera. That's going to be too cumbersome. Numeric summaries are just kind of short bullet points. Okay, we say average age, it's about 20 years old. When we're talking about kind of the diversity in ages, we would say, is there a lot of diversity in the ages that we see in the classroom or not? Not a whole lot of diversity, because most of the people here are between 18 and 25, okay? How many people do we have outside of that age range? We have a few, but not a ton, okay? Just imagine people at the supermarket, okay? What kind of ages will you see of people at the supermarket? You're going to see all sorts of ages, okay? You've got little kids going with their parents shopping, you've got parents, you've got young people who need their stuff, old people who need stuff, okay? You go to any sort of, a Target or a Walmart, you're going to see all sorts of ages of people there, okay? All right. Contrast people shopping at Target and Walmart and the types of ages you see there versus shopping at a store like Hot Topic, okay? All right, for those of you who don't know, Hot Topic's a store at the mall, okay? And their primary, their target demographic is teenagers, people sub 25, really, okay? Their target audience is teens and young adults, okay? They're not trying to sell merchandise to retired folks. They're not trying to sell merchandise to grown-ups, okay? Or older people, they're not, okay? Their target demographic, young kids. So, if you're thinking of that, we can describe the types of ages we would see there. Okay, numeric summaries are useful rather than just saying, there's a wide range of ages here and a small range of ages here, or the ages are older here and they're younger over here. Whatever we're talking about, rather than kind of having these fuzzy descriptions, we can use straight numbers to exactly quantify what we're saying, okay? So rather than saying, imagine at the Olympics for like gymnastics, right? People are scored with numbers. Can you imagine if rather than numbers they just said good or pretty good or not that great, okay? How would we rank our contestants or our competitors? It would be difficult, okay? And so that's all we're doing, is we're just taking something and we're assigning it a number, okay? And we have rules for assigning numbers, just like judges, they assign numbers, and they use those numbers to kind of rank and quantify things. Okay? So we have numeric summaries for center. Okay? Numeric summaries for center tell us where the center in our data set lie. Okay? And so we have things like the mean and the median. The mean is the balance point of our data. imagine, I left this dot plot up here. Imagine this is like a seesaw, or a giant plank, okay? And each of these are 10-pound bricks, okay? And I want to balance this thing so that the plank is balanced, like a seesaw. Where would I put the fulcrum, or where would I put the little triangle so that this thing stays balanced?
About 74.
Okay? So, would I put it over here?
No.
No, if I put it over here, what's going to happen to the plank? It's going to fall like this. Would I put it over here? No, it's going to fall that way. So, just kind of eyeballing it, looks like somewhere around here-ish. Okay, I don't know. But it looks like if I put it around there, maybe it'll look like it will balance, and we could tweak it. I don't know. Okay, this is just an eyeball guess. I have no idea if this is actually going to be balanced there or not, but it looks like it might balance somewhere around there. Okay? This is the mean. Yes? You have a question? You're stretching or raising your hand? Okay. So where you balance the data, that is the mean. Okay? This I just eyeballed looking at the graph here. To actually calculate the mean, I think you guys learned how to do this already, but to calculate the mean, you add up all the numbers and you divide by how many numbers you have. Okay? So to calculate the mean, add up all numbers, then divide by how many you have. That's how you get the mean, okay? We want to do a formula. The symbol for mean is going to be x bar. X bar represents the mean of a data set. Okay? This is mean of a data set. So x bar is the mean, and we find this by adding up all the numbers. So this means add all the x's, or all your numbers. This sideways m is sigma for sum. And then divide by how many numbers you have, that is n. N is equal to the sample size, or how many numbers you have. So we could find the exact value of the mean by adding up all of our numbers and dividing by how many we have. That would be the actual mean. Okay, so that's finding the mean. Is that okay? The median. This is the halfway point. Median, this is half of the data is larger than the median. And half is smaller than the median. All right, so let's say we've got,
77.
what's that?
77.5.
Is that what you found to be the mean up there? Or are you talking about?
How about the mean?
Okay, okay. So I misestimated the thing, all right? So if you add it up and you divide by that, you get 77.5. That would be where it's truly balanced. Thank you. All right, the median, to find the median, the first thing you need to do is take your set of data and arrange them from least to greatest. Okay. Then find the middle number. That's it, okay? If you have an even number of numbers, then it will be, there will not be an actual middle number. Your middle number will be, your median will be between the two middle numbers, okay? Have an even sample size. Median will be between the two middle numbers. Will be, I'll say, halfway between two middle numbers. Okay. So if you have 10 numbers, the median is going to be the spot where 5 numbers are smaller and 5 numbers are larger, okay? And so if you arrange them from least to greatest, it will be between the 5th and 6th number. That's where your median is going to be, okay? A tip, or one way to find the middle number, one tip that you don't have to use, is that the median will be in the n plus 1 divided by 2 position. Okay. The median is not n plus 1 divided by 2. It's the number in the n plus 1 over 2 position. Okay, so let's try this out. Let's say I have 12 test scores. And the test scores are 7. Okay, so these are, oh, did I say 12? Let me come from 2 more. Okay, so these are 12 test scores. Let's find the median. Okay. First thing we do, what do we do? Least to greatest, okay? So I'm going to arrange these from least to greatest. So I have 42, and then I go 58, 65, 67, and what? 70, 72? 70. And then a space here. 70, 72, 78, then 85, sorry, 88, 90, 91, and 100. Did I get everyone? 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah. Okay, 12. So I've arranged them from least to greatest. So what is my n? How many, my sample size is n equals
12.
12, okay? So when you have 12 numbers, it's easy. The median is going to be what? The spot where 6 are smaller and 6 are greater.
Right.
Okay? Or, if we want to use this thing, optional, the median is going to be in the n plus 1 over 2 position. So n plus 1 divided by 2 is going to be what?
6.5.
6.5. Okay? Okay, so n plus 1 over 2 is 6.5. So if I rank these from least to greatest, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sixth place number is 72. Seventh place number is 78. The number in the 6.5 position is going to be between the 6th and 7th number. So the median is halfway between 72 and 78. How do I find that? Okay.
Take the 2
Yeah, I would
divided by
split the
2.
difference. I would just do, I'm going to do 72 plus 78 divided by 2, and I get 75. So my median is 75. Is that okay? Are there any questions? Okay. So let me extend this one more step. Okay, so far we've been talking about numeric summaries to find center. We have the mean, we have the median. The mean, you add up the numbers and you divide by n. The median, you arrange them from least to greatest, and you find the number where half are larger and half are smaller. Okay, and if you got an even number, you're going to find the spot halfway between the two middle numbers by taking the average of the two middle numbers. Okay. I want to bring up the topic of quartiles. Okay, the median is where half are larger and half are smaller. Quartiles, we've got 4 of them, but we really only discussed 3 of them. Okay, quartiles, the first quartile is where 1/4 of the data is smaller. The second quartile is where 2/4 of the data is smaller. The third quartile is where 3/4 are smaller. And the fourth quartile is where 4/4 are smaller. Okay. What do we call the second quartile? Already. The second quartile is the median. The median is where half are smaller, right? So the second quartile is where 2/4 are smaller. 2/4 is the same thing as 1/2. So the second quartile is the same thing as the median. Do I need to say that again, or write that on the board? So let me talk. Can I erase this over here? Sure. So let's talk about quartiles. So the first quartile, 1/4 of the data is smaller than the first quartile. And for the third quartile, 3/4 of the data is smaller. Okay, so Q1, or the first quartile, is the spot where 1/4 of the data is smaller. Okay, in Q3, our third quartile, spot where 3/4 of the data is smaller. Is that explanation okay so far? Okay, so in a set of 12 numbers, like I've got 12 test scores, how many numbers will be smaller than the first quartile?
Can you repeat that?
So in this set, I've got 12 numbers, right? 12 test scores. And I said the first quartile is where 1/4 of the data is smaller, okay? So how many data points, or how many test scores are smaller than the first quartile in this set? Yeah, 3, right? Because 1/4 of 12 is 3. And so it's going to be the spot where 3 numbers are smaller. Does that make sense? Okay. And so what will be the value of my first quartile?
1458.
Okay, so sorry, this is not the, these are the raw test scores that we've already arranged over here. So how many numbers are smaller? 3 of them. So my first quartile is not 65, but it's right there. Q1, okay? Is that okay? And so Q1 takes on the value 66. Okay, I would do 65 plus 67 divided by Q. Q1 is equal to 66. Okay? Another way to look at this, if somebody asked you to split a sandwich into quarters, how would you do this? You'd first cut it into half, and then you'd cut each half into half again, right? And you'd get quarters. Okay? So if we have 12 numbers, we can find the median, and that splits our data in half. Once we have half the data over here, we can just split that in half, and we get quarters. So over here, I've got half, and I could just split this in half, and I would get quarters also. Okay? So another way to find quartiles is to first find the median, and then after you find the median, take each half of the list and find the median of that. Okay? So to find quartiles, find the median, then take half the list, and find the median of each half. The quote-unquote median, which is actually the quartiles, so don't shout out your answer, but I want everybody to find the value of Q3 for data set. All right, do we have a value? 89. Q3 is 89. Okay, so for our data set, the median is 75, Q1 is 66, and Q3 is 89. Okay? These all give us an idea of where our data lies. Okay? It gives us an idea of the middle. The middle would be our median, and then it also tells us kind of where the where the middle half are. Okay? How much of the data is between Q1 and Q3? 2 quarters, right? So each basically, every time I'm drawing a break here, that's a quarter of the data. And so I've got 2/4 of the data between Q1 and Q3. So I've got 50% between Q1 and Q3. How much is between Q1 and the median? 1/4. How much of the data is larger than Q3? A quarter. Good. Yeah. Okay. So we have that. Let's take a short break. 10 minutes, no longer than that.